Okay. Today we are going to look at chemical equilibrium. In our previous lesson, we talked about rates of chemical reactions, and we also calculated the rate of some chemical reactions. We said the rate of a chemical reaction is the speed of the reaction, or the rate at which reactants are being converted into products. Today we are looking at chemical equilibrium. We have a lot or several examples of equilibrium in our everyday life. For example, if you are running on a treadmill, you are in a constant motion. However, you are not moving forward or backwards. So when you run forward, the treadmill is also moving you backwards. That is one example of equilibrium. Another example is when you boil water in a pressure cooker. What happens is that the water is being converted to vapor, and the vapor at the same time is being converted back to liquid water. That's another scenario. So what then is chemical equilibrium? To define chemical equilibrium, we need to ask ourselves some important questions about reactions. So I'm going to ask you these questions. Does a reaction always run its full course so that all the reactants are used up? In a chemical reaction, is it always the situation that reactants are always used up?
No.
No. Okay. Who else? Or everyone is accepting the no? Okay. Who answered that no?
Says me.
Your name?
Gidiselom.
Okay, Selom. Do you know any reaction in which the products are not used up, or any example or scenario? Or you just said no? Okay, no problem. Let's continue. So it's true. We'll find out why not all reactions have their reactants being used up at the end of the day. So it's true. So not all reactions go to completion. Then the second question is that does a reaction always proceed in the same direction, or can it be reversed? You always have a situation wherever we have reactants, it must by all means give us products, and then there is no way we can reverse the product back to reactants. Is it always the case?
No.
Okay, that's also true. So we have other scenarios where after getting products from reactants, we can reverse the reaction and get back our reactants. So reactions that go to completion are called irreversible reactions. We can't reverse them. Then reactions that do not go to completion, that is the process continues, we call them reversible reactions. Okay. So to define chemical equilibrium, we'll say that chemical equilibrium is the state of a reversible reaction where the rate of the forward reaction equals the rate of the reverse reaction. Okay, so in our previous lesson, we talked about rates of reactions, and in those chemical reactions, we realized that we only have a forward, the reaction going in a forward direction. And we can give several real life examples. For example, when you are burning wood, dry grass or paper, you realize that the wood completely burns, so the reactants are completely changed to products there. Another example is when you are mixing an acid with a metal. For example, you place zinc in hydrochloric acid. At the end of the day, the zinc will be consumed. You'll be forming zinc chloride and hydrogen gas will be released. There is no way you can reverse this reaction. Some other reactions can, however, occur in both the forward and then the backward direction. So in these reactions, none of the reactants is completely used up. And so the reactions do not go to completion. So as I mentioned earlier, these are called reversible reactions. And we have several examples. For example, preparation of ammonia from nitrogen gas and hydrogen gas is a reversible reaction. And then converting solid iodine to gaseous iodine is also another example. Another example is when you combine carbon monoxide gas with oxygen gas to get carbon dioxide gas. Yeah. Real life examples, when you have a bottle of fizzy drink, for example, Coca-Cola, in the bottle you have carbon dioxide dissolved in the liquid. So there is also carbon dioxide gas in the space between the liquid and the cap. See the top part of your bottle, there is a space there. You also have carbon dioxide there. Yes. So that is one example of chemical equilibrium in real life. Okay. Now let's move to the concept of equilibrium. So we say chemical equilibrium has occurred when a reaction and its reverse reaction proceed at the same rate. So as a system approaches equilibrium, both the forward and the reverse reactions are occurring at the same time. And then when the system reaches equilibrium, the forward and reverse reactions are proceeding at the same rate. Okay, so I have a diagram here where I'm using a pressure cooker. So as I was explaining earlier, you have water in the liquid form being converted to water vapor or water in the gaseous state. In a very closed system like this one, your reactants will never get consumed. It means you still have the liquid water there boiling forever. So this is one example of a system in equilibrium. Okay, now let's see how we can depict or show equilibrium using chemical equations. So as we mentioned earlier, if a system is at equilibrium, both the forward and the reverse reactions are being carried out. As a result, we can write, for example, if this is a reaction from an N2O4 to NO2, they are both gases. This is a reversible reaction. We can write the equation using this arrow, telling us that this system is at equilibrium. So the forward reaction and then the reverse reaction are occurring at the same time. So graphically, we can use this to demonstrate. So we have the blue curve telling us N2O4, which is a colorless gas, is being converted to NO2. Then at the same time, NO2, which is a brown gas, is being converted back to N2O4. At a point, you realize that the two graphs will meet. In practicality, there will be a point where you wouldn't see a change anymore. So the two colors will even mix together. You won't identify the colorless and then the brown gas. So on the graph, you see this point here where the two curves meet. That is your equilibrium point. Okay. So if we should split the equation, this equation, if we should split it into forward and reverse reactions, we'll get the first equation this way, and we have N2O4 going to 2 moles of NO2. So the rate law will be the rate for the forward reaction, and I think we did this in our previous lesson. So we are looking at the reactant here, so the concentration of N2O4. So we are assuming that this reaction is an RDS reaction. So in all our calculations, take note, our reactions will be considered as RDS. Okay, so here the number of moles here is 1, so we didn't raise to any exponent here. Now the reverse reaction will be NO2 going back to N2O4. So here our reactant now is NO2, and it has 2 moles there, so its exponent will be 2. So the rate law will be Kr, that is K reverse, times the concentration of NO2 raised to the power 2. Good. So at equilibrium, in our introduction, we said at equilibrium, the rate of forward reaction is equal to the rate of reverse reaction. So we are trying to work out a constant in this topic or this lesson that we call the equilibrium constant. So what we are going to do here is, once we have established this fact that the forward reaction is equal to the reverse reaction, then we can rewrite this expression like this from what we had here, saying these two equations are equal. So then we have that being equal to that. So if we rewrite the whole equation, that is, you initially divide by Kr and you work it out, and then you come across this. So you have K forward over K reverse equals to the concentration of NO2 to the power 2 all over the concentration of N2O4. Any questions so far? Are we all following?
Yes.
Good. That's nice. So let's move to the next slide. So we can now generalize and write that the equilibrium constant, that is K equilibrium, can be written as the Kf over Kr. That is the rate at which we have the forward reaction going over the rate at which the reverse reaction is going. So we want to generalize an expression or a formula that we can use to calculate the equilibrium constant. So we are considering a hypothetical equation. When we say hypothetical reaction, a hypothetical reaction is just an example reaction. This is not real. We are just using symbols here. So this reaction, we have A moles of reactant A plus B moles of reactant B going to C moles of reactant product C plus D moles of product D. At the same time, this can also become a react when you are going the reverse direction. So there you have C plus D going to A plus B. So based on what we have derived so far, the equilibrium constant in terms of concentration of the species or what we are using will be the forward. This we have the reverse rather over the forward. Let's go back to. So we have C, concentration of C to the power C times the concentration of D to the power D all over concentration of A to the power A times the concentration of B to the power D. Okay. So let's move to the next slide. So we have another expression for the equilibrium constant. Sometimes in chemistry, we deal with gases. So instead of talking about the concentration in terms of mole per dm cube, we can also talk about the concentration of the gases in terms of pressure. So we have this expression. Okay, I think let me check. Let's see here. Okay, Michael Fosu says he doesn't get the previous slide. Is it this one? Okay. So here we are talking about let's go back. I think from this direction, when we made kf over kr the subjects, we rather got the product here, or the reverse over the forward. Are you following? The reverse over the forward. So that is why when we come here, we also have the reverse over the forward reaction. I hope you are following. Fosu. So let me go to the next slide and explain. Yeah. So I think it's this slide. Fosu, are you okay now? Okay, that's good. Yeah, that's a good question. So whenever you are not getting anything, please alert me, because we will need all these theories, generalizations in our next slides or in our calculations. Okay. So let's move on. What's happening? So we are talking about the equilibrium constant in terms of pressure. So here we use partial pressures. So when you see Kp, means you are referring to the equilibrium constant in terms of partial pressures. So let's try and get a relationship between Kc and then Kp. We know from physics and chemistry, when you are dealing with the ideal gas law, PV equals nRT. If we rearrange, trying to make pressure the subject, we will get P to be equal to N over V times RT, where R is the molar gas constant and T is temperature. P and V are pressures. So with this in mind, we can then express Kp, which stands for equilibrium constant in terms of pressure, and Kc using this equation. We know N over V gives us concentration, right? Concentration is equal to N over V. So we can rewrite this equation as Kp. Here was P, pressure. So the equilibrium constant in terms of pressure can be equal to the equilibrium constant, in terms of concentration times RT all to the power delta N. Delta N stands for the change in moles of the gaseous product minus the moles of the gaseous reactant. So this expression is very, very important. We'll be using it in subsequent calculations. Okay. Are we okay so far?
Yes.
Yes.
Good. So let's move on. Now, I should have left this out. So what does Kp and Kc represent? How will you explain Kp and Kc? Any idea? Before we move on.
Sir.
Yeah, who's talking?
Hello.
Elom, okay,
Hello.
Elom. Yeah, good.
Kp is the pressure or the partial pressure of a reaction.
The equilibrium constant in terms of partial pressures, right?
Yeah.
Okay. What about Kc?
Kc is the concentration.
Okay, so the equilibrium constant in terms of concentration. Okay. Who else? Yes, we want another answer from someone else. Okay, let me call some of us here. Akposwe.
Sir.
Yeah, how will you define Kp and Kc?
Sir, the Kp is the constant of pressure.
The equilibrium constant in terms of pressure, okay?
And
Okay.
the Kc,
Mm-hmm.
the equilibrium constant in terms of concentration.
Okay, good, good. Let's call one lady or two ladies. We've called two guys. So, Lisa.
Kp is the equilibrium constant of pressure in terms of pressure.
Okay.
And Kp is the equilibrium constant in terms of concentration.
Okay, good. Is Salma a lady?
Yes.
Okay, Salma, let's hear you.
Kp is the equilibrium constant in terms of pressure, and Kc is the equilibrium constant in terms of concentration.
Okay, good. So we can also say Kc represents the equilibrium constant when equilibrium concentrations are expressed in molarity, that is Kc, whilst Kp represents the equilibrium constant when equilibrium concentrations are expressed in atmospheres. So yeah, I'm using the units. So atmospheres or Pascal, but normally we use atmospheres. We use ATM or atmospheres. Okay, now let's look at the next slide. I think it will tell us okay, so I think, yeah. So Kc represents the equilibrium constant when equilibrium concentrations are expressed in molarity, that is concentration as we're saying, then here in terms of pressure. Okay, so we are looking at our first worked example here. So in the synthesis of ammonia from nitrogen and hydrogen, we have this equation. So nitrogen gas plus 3 moles of hydrogen gas gives us 2 moles of ammonia. And this is a reversible reaction. So we are to calculate Kp for this reaction at a temperature of 300 degrees Celsius. And then there are some constants given to us here. We have the molar gas constant, 0.0821 atmospheres dm cube per Kelvin per mole, and then Kc is 9.60. Here they've not given us a unit for Kc. So let's see how to go about this. So the first thing we have to do is, we all know the formula. Here is supposed to be delta N. I omitted that. Forgive me. So we first calculate the change in number of moles. So we said it should be products minus the reactant. Products minus reactant. So when we look at the number of moles at the product side, we have 2. Then the number of moles at the reactant side will have 4. So this gives us 2 minus 4, giving us negative 2. Okay. So remember that the question was talking about the synthesis of ammonia from nitrogen and hydrogen. So it means we are looking at the forward direction, although the equation is at equilibrium. Good. So the temperature should always be in Kelvin, because if you look at the molar gas constant, it has its unit having per Kelvin in it. So once we have per Kelvin here, it means when they give us the temperature in Celsius, we have to change it to Kelvin. And to change the temperature from degree Celsius to Kelvin, we just add 273 Kelvin. So we added 273 to 300, we got 573. Then you substitute the values into the expression we derived relating Kp to Kc. So we have this. I should have plugged in the units for you to see, but in the next question I'll show you how you get the units. So here, if you just punch in these values, you get 4.33 times 10 to the minus 3 atmosphere to the minus 2. So what happened was, we have 9.6. This should have been in a unit, escape me, and then we have this one, the units is here. So when we plug it in, it will cancel out somewhere. So when we go to the next exercise, the units for Kp and Kc when you are given questions. The units for the equilibrium constants are not constant. Although they are constants, the units are not constant. They change. They depend on the number of moles of the products and the reactants. So they will keep on changing. Are we okay with the calculation so far?
Yes.
Yeah.
Okay, so when you plugged in, you got the same values, right? Or you didn't check? Did you check with your calculators? Hello? Okay, let's move on.
Yeah.
Okay, good. So I'm going to leave this one for you. Yeah, to solve this one.
Check.
Yeah, hello. Yeah, so this is our exercise. We have this reaction, SO2 gas plus oxygen gas giving us SO3 gas. This is also reversible. We have to give an expression for Kc and then an expression for Kp in terms of Kc. So the first one, we are just looking at how you write the expression for Kc using the concentration or the moles, the number of moles here, as we learned in the previous slides. Then for the second part of our question, you are just supposed to write Kp in terms of Kc. That is the relationship between Kp and Kc. That is the equation you are looking for. Then the last part of the question, you are doing a calculation there. So let's try hands on this, and then when you are done, you tell me your results. So I think we can do this in 6 minutes at most. Are we done with the I part of the question? Who is done with the I part?
Yeah.
Who?
Semi.
Okay, your name.
Elom.
Okay, Elom, let's go.
Elom.
Yeah, give us the, what did you get?
Say Kc equals. Say I get like into brackets SO2 brackets close raised to the power 2 brackets open O2 then brackets close all over brackets open SO3 bracket close all raised to the power 2.
Okay, that is your answer. Let me put it down. Who else got an answer for I? So Elom gave us Kc to be concentration of SO2 to the power 2, concentration of O2 all over concentration of SO3 square. Who else? Nanama. Nana Ama.
Yes, please.
Are you done with
Please,
the I? The I, just the I. Roman number 1.
No, please.
Wow. Actually,
I had some connection problems. I'm now.
Okay. Okay, maybe let's go to the previous slide for you to get the revision. So we said that for you to get Kc, you have to find the concentration of product over the concentration of the reactant. So that is using this equation. So this becomes our a generalization. That is our working formula. Any reaction they give you, you have to use this idea, this concept. So it's always product over reactant. Nanama, you get it?
Yes.
Good. And then always look at the number of moles there. Okay. So I think with this, we should all be ready with our answers. So let me call another chemist, Lisa.
Okay, sir.
Yeah. Hello, man.
Yeah.
Okay.
So the first one.
Yeah.
Bracket open.
Mm-hmm.
SO3 bracket close all raised to the power 2.
Okay.
Then bracket open. SO2 all raised to the power 2.
Okay.
Then
So
bracket open. O2.
okay. Okay. So you've changed your answer now.
Yes.
Okay. Accepted. So Lisa Kise. What's your result?
Kc is equal to bracket open SO3 raised to the power 2 all over bracket open SO2 raised to the power 2 bracket close before raised to the power 2, then bracket open O2 bracket close.
Good. Now, which type of brackets are you using?
The square brackets.
Excellent. Excellent. Because you are talking about concentration. So you should employ the square bracket. Good. I believe we all got the same results. Let me find out from some random people. Kwansa Herbert Mensah. What did you get for I? Mr. Herbert. Hey, Mr. Herbert Mensah. Okay. Mr. Michael Busu. What did you get for the I?
So I got equilibrium constant of, in terms of concentration, is equal to square bracket SO3 bracket close squared all over square bracket SO2 bracket close squared another square bracket O.
Okay, that is good. I think we are doing well. Let's look at the second part of the question. By now we should be done. What is the expression for Kp in terms of Kc? Yes. Let me call Amankwa Yebua. Yeah. I. What did you get for I?
I had EC into brackets RT or.
Tell me again.
I said I had KP is equal to KC into bracket RT
Okay.
exponent -1.
Okay, that's good. Excellent. I believe you all got the same result.
No.
Okay, Akosue, right? What did you
Yeah.
get?
I didn't get it too.
But what did you get? Or you were not able to attempt it at all?
Yes.
Okay, so let's go back to the previous slide. We'll get that there. You see this relation? Yeah. So this relation is a relationship between Kp and Kc. So means you need to keep it in your mind. I think we proved it from this the ideal gas equation or the ideal gas law. So this is a very important equation you need to keep. Even if you forget, try to prove it. You can memorize this easily. So you should write it down. You'll be using it to solve a lot of questions. So it's important for you to write it down. So I think when you come to our problem, here, our Kp should be equal to Kc to brackets RT. Then the delta N stands for the change in number of moles. So here it should be product minus reactant. So if you look at the number of moles at the product side, you have 2. Then the number of moles at the reactant side, you have 2 plus 1, giving you 3. So 2 minus 3 should give you negative 1. Okay? Are you okay now? Akweswe? Akweswe? Yeah, okay, good.
Yes.
Let's try the third one. We have to calculate the value of Kp. So here, you are using the expression you derived here. The expression you derived here. And then you just substitute or plug in the values. You know R and room temperature. What is room temperature? Who knows room temperature? What's the value for room temperature? The average room temperature.
So 273.
Yeah. That is not correct. Anyone
Sir.
else? Yeah.
298 298K.
Good. Very good. So in Celsius it's 25 degrees, right?
Yes.
Good. So don't forget room temperature is 25 degrees Celsius. Then the normal body temperature is 37 degrees Celsius. So here they are assuming you know room temperature. The average temperature of your room is 25 degrees Celsius. So you convert that to Kelvin and plug it into the expression for Kp. And then you get your result. Then also take note of the units used. So if you look at the units, you have the molar gas constant given to you in joule per mole per Kelvin. If you look at your values here, you have decimeter cube. So decimeter cube or meter cube here doesn't go with joule. So you need to change the joule there to Newton meter. I guess you know 1 joule is 1 Newton meter from physics. So if you are not aware, 1 joule is equivalent to 1 Newton meter for you to get the right unit. So the joule should be changed to Newton meter. Then if you look at the concentration, we were given the concentration, or sorry, the Kc rather, this Kc. A Kc value in decimeter cube per mole. You have to change the 3000 dm cube to meter cube.
Enya, but that was the other fumaro.
Akboswe, your mic is on. So take note of, so we need to convert the decimeter cube to meter cube.
Won't you buy the Wi-Fi today?
So if I move, you see 345.
LS were being released.
You should have removed them.
Look, you see the merchants, they collect this thing. So they will subtract 3 CD.
Hey, but this one in this one CD.
Where is that?
CD. 300.
Lisa, your mic is also on. You are hearing some 3 CDs. Are you doing business maths or chemistry? Who is done? Nanama, are you done? Your microphone is on. You are running away. Nanama,
Yes.
are you done?
No, please.
Okay.
Please.
Mm-hmm.
Can you explain why the joule doesn't go with the decimeter?
Okay, we are talking about pressure here. So pressure is in Pascal or atmospheres, okay? And then 1 Pascal is also equivalent to Newton meter, right? That would be Newton meter square. Newton per meter square. Pressure is force over area. Is that also?
Yes.
So force is Newton and then area is meter. So 1 Pascal should be 1 Newton per meter square. So we want our, because of the Newton and then meters there, we want to convert the joules to Newton meter. Are you getting it?
Yeah.
So that is the reason why we need to do that conversion. Wow, this has taken us a long time. Let's do it together. Or Come again.
Let me try.
Okay, good. So you have, let me give you guys 2 minutes. 2 minutes. Okay.
1.211.
Uh-huh.
I said 1.211
Okay.
times 10 raised to the power negative 3
Come
and
again.
raised to the power negative 1 meter square.
Come again.
1.1
Mm-hmm.
times 10 raised to the power negative 3
Mm-hmm.
Newton raised to the power negative 1 meter square.
Okay. So what's your name? Elom, right?
Yeah.
Okay. Good. Who else? Okay. Temperature for Kelvin. The room temperature is 25 degrees Celsius. So add 273. So you have 25 plus 273. You get 298 Kelvin. That will be the temperature you'll be using. Anyone else? Okay, so our time is up. So Akwaswe, Elom, your answer is correct. Let's look at the standard solutions. So I've written my reaction here again in order to get a number of moles. So we have Kc being equal to this. I think we discussed this already. Then with our Kp, this will be our expression for Kp. So we now do the plugins. We know that Kc is 3000 decimeter cube per mole. So as I mentioned earlier, your value here should be changed to meters cube, and 1 dm cube, 1 meter cube is equivalent to 1000 dm cube. 1 meter cube is equivalent to 1000 dm cube. So when you change, you get 3 meters cube per mole for the equilibrium constant in terms of concentration. Then your temperature here is 25 degrees Celsius. That is room temperature. So you change it to Kelvin by adding 273. You get 298 Kelvin. Then the molar gas constant. So instead of joule per mole per Kelvin, we have Newton meter per mole per Kelvin. That's the only change there. So when we substitute, I have this expression, RT exponent -1 is the same as 1 over RT. So that's what I have here. So I have my Kc here, which is also here. That is 3 meters cube per mole. Then times 1 out of 8.314 Newton meter per mole per Kelvin times 298 Kelvin. So you can see clearly that 3 will come to the top because 3 times 1 will be 3. So you should have, with the values, let's work out the numbers first, the values. So we have 3 divided by 8.314 times 298. So that will give us 1.21, yeah, 1.211 times 10 to the minus 3. Then let's talk about the units. All this expression will come to the top there. So meters cube here, you have 3 minus 1 here using the laws of indices. So you get meters squared. Then per mole will cancel per mole. Per mole will cancel per mole. Then you have I think I left out one thing. This is per mole per Kelvin. Yeah. Sorry. Our Kelvin is supposed to vanish somewhere. Okay. So we have per Kelvin here also taking care of this Kelvin. By the law of indices, we have -1 plus 1 giving us 0. So eventually you arrive at this answer. I hope you are okay with this.
Yeah.
Are you all okay? Elom is okay.
Yeah.
What about the
Yeah.
rest of you? We are all okay, right? Okay. So we are moving to the next problem. Unfortunately, I solved this one. So with this, we've been given the concentrations of the reactants and products. So with this question, we have to write our own chemical equation and calculate for Kc, which I have done already here for you. So with this, I have the unit in per molar, which is the same as mole per dm cube, always the power -2. So I've done this part for you. So I'm giving you the next one to do. You have to calculate the Kp of the reaction in exercise 3. If you are given that the molar gas constant is now 0.082 atmospheres per dm cube per mole per Kelvin. So you are still using the same question here to solve question 4. So you are calculating the Kp. So let's try this one too. Are we all following so far?
Yeah.
Okay. If you have a question, you can text me or you can send a message. Yeah, who is done? So you are just using the relation Kp equals Kc into bracket RT raised to the power, change the number of moles. You calculated Kc here, so you just substitute it into the equation.
So let me try.
Okay.
So 5.3
Yeah, continue.
So I'm coming.
Okay.
I'm coming.
Okay. So with this one, the only thing you have to change is you change this to mole per dm cube, the molar, so that you can use it to eliminate this, and then perhaps this.
So I'm confused. Oh.
Where is the confusion?
So how to change the molar to the decimeter cube?
Okay, molar is simply, this one is even in core science. When you see big M, it's the same as mole per dm cube. Okay, are you okay? So like this big M like this, just replace the big M with mole per dm cube. That is mole, then you have dm raised to the -3. Then all of it will be again raised to the power -2. Are you okay? Who is done? Michael, are you done? Michael.
Second try.
Okay.
Say 12 point.
Okay, 12
Say
points.
12.927
Mm-hmm.
mole raised to the power -3.
Okay. That is all.
Yeah.
Okay, this is Elon, right?
Yes.
Nice try. So let's take another. Lisa, are you done?
Please, no.
Wow. I know these questions are quite tedious. Salma.
Please, no.
Yay. Nanama. Someone is asking for temperature. (500K), 500 Kelvin. Okay, our time is running up. So let's solve it together. So we'll have to start with this relation. I believe you all started this week. KP KC RT delta N, and I've already solved for my delta N. That is the change in number of moles. So with that, so let's look at that from the balanced equation. That will be 2 minus 4. 2 minus 4. So giving us -2. So I have my Kc. We calculated that as 1.06 times 10 to the power 3. So and that value there has the units. The -2 is affecting only the unit. So that is molar raised to the -2. So what I did here was to rewrite the molar as mole per dm cube, and then raise it to the power -2. So it will go to affect only the unit. Then my molar gas constant is what is here given to me as 0.082 atmosphere dm cube per mole per Kelvin. So you multiply that by the temperature given to us in the question, which is 500 Kelvin, all to the -2. The change in number of moles is -2. So I try solving, because multiplication is commutative, so I can rearrange it anywhere I like. I can rearrange this. Mouse is freezing. So I multiply the whole number, or the numbers first. I had 1.06 times 0.082. But I remember 0.082 is multiplying 500. So you multiply that 0.082 times 500. You get, I think you get 41. Then you raise your answer to the power negative 2. You get 5.9 something times 10 to the minus 4. Then you multiply that by 1.6 or 1.06 times 10 to the power 3. So that gives us 0.30577. So you round it to 3 decimal places, you get 0.631. And then let's look at the units. So with the units, whoa, mouse is freezing here. Hello, can you hear me?
Yeah.
Yeah.
Yes.
Fortunately, my pointer is a bit free. Okay, I have to get them. So with the units, you realize that atmospheres will be raised to the -2, and then your decimeter cube will be raised to the -6. That is for this one. Yeah. Then the other side, you have decimeter raised to the +6. I think with this ones you can. So when you're applying this, you realize the dm to the 6 multiplied by dm to the -6 will give us dm to the 0. So in effect, that will go off. And then our Kelvin will also be raised to the power 0. That will also go off. And then our mole to the -2 will also eliminate our mole squared. So we'll be left with 0.631 atmosphere to the -2. Is it clear for everyone?
Yes.
2.
Good. Excellent. So let's take this one. If you aren't able to finish time, I think we have about 3 minutes or so. We'll use it as homework. So let's try. We have this, and then we've been given Kc. So we have to calculate for Kp. I don't know what is happening to the mouse here.
bracket close. Yes. Hello, sir.
Yeah.
So can you move to the next slide, the one we are coming to work on?
Okay, sorry. Reason. Wow. Excuse me. Okay. Need to get a mouse.
So let me try.
Yeah. Yeah, we are listening.
3.33 ATM
3.3313 ATM. Mhm. Continue.
So I'm talking 3.3313 times 10 for 8 to the power negative 1
3.3313 times what?
times 10
10 to the power.
negative 4.
Okay. Units.
ATM Kelvin raised to the power negative 1.
Okay. Who else? How? Okay. Our time is up. So let's, yeah, Lisa.
Please, I had 3.331 times 10 raised to the power negative 4 dm 6 raised to the power 6 mole raised to the power negative 2.
DM raised to the power 6, right?
Yes, please.
Mole to the power.
Negative 2.
Okay. Who else? Let me look at the solution together.
Let's see. It's not charging on. Why? This is not working. 1 minute, 3 minutes left.
Okay, let's go. So we already know KP is KC RT delta N. So we first have to calculate the change in number of moles. So I think that will be 3 minus 2. So this one will give us 1. Give us positive 1. Okay. Amankwa has also sent his answer. Okay. Good. So here we plug in the values and we solve. Get 0.033. So if we should write this in standard form as you guys did, that will be 1, 2. So it should be to the power times 10 to the minus 2. Or let me check whether I did an error somewhere, because my answer is different in terms of exponent from most of you. Let's see what Yobua got.
Sir,
Yeah.
please, you forgot the K for the 1069.
Okay, the temperature.
Yes.
I didn't bring the
Other K.
the other key. Okay. Aside that, the values, there is difference here. Like, you didn't get 0.033, right?
I had 3.331.
Yeah.
Raised
Times
the
10
power 84.
times 10 to the power negative 4.
Yes.
So this is different from what I had here.
Yes.
So what went wrong? So this is a Kc value. This is our molar gas constant, 0.0831. Then this is the temperature, 1069. So let me punch it again, 3.75 times 10 to the minus 6, all times 0.0831 times 1069. Okay, yeah. So I think I had an issue. So it should be 3.331 times 10 to the minus 4. Yeah. Times 10 to the minus 4. Okay. So let's look at the units. The units will have decimeter to the power 6. Then the mole. I have atmospheres here. So you should check your units. Lisa. Lisa, you need to check your units, okay? So the answer is 3.331 times 10 to the minus 4. We'll look at it together again in our next lesson. I think we'll have to end here. Any question before we close?
No, sir.
Okay, so we'll end here and see you guys in another lesson.